So when we've finished, what we will have done is reviewed the major topics that we've seen regarding the mathematics of decimal numbers. Let's get going. The first thing we talked about when we introduced it was naming decimals. And when we're dealing with whole numbers, we started with hundreds, tens, units. Then we have the decimal point. Everything to the left of the decimal point is greater than 1. Everything to the right of the decimal point is less than 1, and we name it as tenths, hundredths, thousandths. Notice the THS. 10,000ths, 100,000ths, and finally millionths. Of course, you can go past there, always getting smaller and smaller and smaller terms. But typically, this is about as much as you're going to have to deal with, and just as you name the numbers greater than 1 in terms of millions, 10 millions, 100 millions, you can name them equivalently and symmetrically going down, becoming less and less and less by factors of 10. Then we looked at naming decimal numbers. For example, if we write 0.3, that's said as 3/10, and the fractional equivalent is 3/10, 3 over 10. 0.75, that's said as 75 hundredths and written as a fraction as 75 over 100. If we have 0.456, we have 3 digits to the right of the decimal point. We have tenths, hundredths, thousandths, and that would be spoken as 456 thousandths and written as 456 over 1,000. Another thing we looked at is changing decimals to fractions, and we've already spoken a bit about that. For example, 0.375, again, you can say tenths, hundredths, thousandths, and you would write that as a fraction as 375 thousandths. But there's a problem here. That's a perfectly good fraction, but it's not a fraction reduced to its lowest terms. We need to see if there are any common numbers that we can divide the numerator and denominator by to reduce that fraction. 375 thousandths, I see that there's a factor of 5 that I can take from the 375 and from the thousand. So I can write this fraction equivalently as 73 200ths, and that's as far as I can go. The equivalent fraction for 0.375 is 73 200ths. When you change a decimal to a fraction, you should remember that, depending on the problem, you need to then look at that fraction that you've derived from the decimal and reduce it to its lowest terms, the representation for which there are no common factors between the numerator and the denominator of the fraction. Another thing we looked at was rounding decimals, and this works very similar to the way you round whole numbers, except now we work with the zeros differently. For example, to round 3.175 to the nearest tenth, we would put our finger on the 1, which is the 10th place. Then we would look to the right to see whether the number immediately to the right is 5 or greater. If it is, we round up, and then we drop, when we round up, we change the number that the place we're rounding to the next highest number, and then drop all the numbers to the right of that. If that number happened to be less than a 5, then we would round down and leave that number at the 10th place the same, and then again drop any numbers to the right of it. So for example, if that were 3.1 1.35 instead of 175, I would round that down to 3.1 to the nearest tenth. Then we looked at adding and subtracting decimals, and to add decimals, all we need to remember is we line up the numbers that we're adding along the decimal points, and we add these just as we would add whole numbers. 7 plus 5 is 12. I carry the 1. 6 and 4 are 10, and 1 is 11. So I carry another 1. 4 plus 4 is 8. 2 plus 3 is 5. 1 plus 2 is 3. Again, the rules for simple addition of decimal numbers is line up the decimal points so that you're adding tenths to tenths, hundredths to hundredths, and so forth, and just make sure that your decimal points are lined up, put that decimal point down in the same place in your answer, and just keep going. Then, as I said, you just treat this like whole number addition. Subtraction works exactly the same way. We can prove all of this by changing the decimal parts to their fractional equivalent, but we really don't have to. What we just need to remember here is when you do a subtraction, you do it exactly the same way. You line up the decimal points and you subtract then just as you would whole numbers. Line up the decimal points, just do a regular subtraction. There really isn't any mystery here. Now let's look at something just a little bit more complicated. Let's talk about adding and subtracting signed numbers. The case we have here is 0.0037 minus 1. This might look a little difficult for a couple of reasons. First of all, we need to remember all of the procedures for signed numbers, and that is the idea that we subtract the smaller absolute value, we disregard the sign, from the larger absolute value, and then the result, the answer, has the sign of the larger of the two digits. In this case, we want to subtract 0.0037 from 1. But the problem is 1 doesn't have any decimal points written with it. But remember that you can always add zeros to the right of any number past the decimal point. So we make 1 into 1.0000, and that will let us do that subtraction. When we do, we notice we're going to have a cascade of things that we need to borrow, ultimately till we get to the 1. For example, 0 minus 7, I can't do it, so I'll borrow a 1 from the tens place. So if I do that, I have 10 minus 7 is 3, but then that 0 becomes a 9 because I've borrowed a 1 from the place to the left of that. So 9 minus 3, having borrowed that, is 6. Then that's a 0, but I've already borrowed 1 from the place to the left of that. That becomes a 9. Then I borrow a 1 from the 1, and that becomes a 9. The decimal point goes down, and now I have to, of course I can put a 0 here because there's nothing left from that 1. Now I see that the 1 is the larger of the absolute values, and its sign is minus. This just has to do not with decimals, but with adding or subtracting signed numbers, and now I'm finished. The result is minus 0.9963. The next thing we did was look at using decimals with adding and subtracting polynomials. Here we have a couple of polynomial expressions, one subtracted from the other, and we need to remember a few things. First, we need to remember that this is a subtraction, and we need to line up the numbers and again put in the correct decimal places where we don't have them so that we can be able to do this. I see that in the 42, in the object I'm subtracting, I need to put in decimal places at the 24, and I see I need to put in decimal places at the 42 in order to do that subtraction. Now I remember something else. In order to continue here, I need to take that minus sign inside the bracket. And to subtract, I need to add the inverse. To get the inverse, I change all the signs. If I see a plus, that becomes a minus. If I see a minus, it becomes a plus. For example now, the inverse of 24z to the 5th plus 7.9z cubed plus 42 is going to be minus 24z to the 5th. I had to change that sign. Minus 7.9z cubed minus 42. Now I'm all set to do the math because I've changed all of those signs. Now I can do that arithmetic, and I basically add 0.0087 to the 42.0000. Then I do that next one as a subtraction, just carrying out the math, and that sign is going to be positive. Then I look at the z to the 5th term, and I do that as a subtraction, subtracting 0.137 from 24.000. But again, since the 24 has a larger sign, the final sign of my result is also negative. This, when you're dealing with polynomials, all you need to do is find the like terms, line them up, and then just do the decimal math with the sign numbers exactly as if you were doing any individual problem, except now you're doing it in the context of a polynomial. And when we multiply decimals, we change the pattern a little bit, and we multiply decimals like we do integers, but now we need to count up the number of decimal places, and the decimal places in the product when we're done is the sum of the decimal places in the factors. Let's remember and take a look at that. Suppose we multiply 5.6 by 3.8. We just continue to multiply those as if they were only whole numbers. Then, just as we do with whole numbers, we add that up. But you see I have a 1 decimal place in the 5.6, 1 decimal place in the 3.8. So in my product, in my final result, I see I have 21.28. I need to count from the right 2 decimal places. To summarize, I multiply them just as I do integers, and then the number of decimal places is just the sum of the number of decimal places in the factors. Now remember that exponents are just an extension of multiplication with the same numbers. So we need to ask, if we're dealing with taking something with a decimal to a power, how do we deal with that? 0.3 cubed, when we work that out, is 0.027. And we can see that there's 1 decimal place here and 3 decimal places in the result. If we take 3.28 squared, we see that there are 2 decimal places here and 4 decimal places in the result. We can say that, we can make a rule then, just a rule of thumb, that if you are taking some decimal number to a power, the number of decimal places is equal to the number of decimal places in the number you're starting with times whatever power you're raising it to. And you can just work this out by doing the decimal multiplications, but it's interesting to know the rule. Another thing we've looked at was scientific notation. This is useful when we have very large are very small numbers. For example, if we have the diameter of the Earth in kilometers, 12,756 kilometers. We want to write that as a number between 1 and 10 times 10 to some power. We start to the right of the 6 and start counting back to get the power until we can put a decimal point between the 1 and the 2 there, 1.2756. Then we write that, and since we've counted back 4, we've reduced that number by 4 orders of 10, and so we need to get that back by multiplying by 10 to the 4th kilometers. If we wanted to, we could round this to the nearest hundredth and still express it as scientific notation 1.28 times 10 to the 4th kilometers, which would be 12,800 kilometers if we were to multiply that out. To divide decimals by a whole number, you just do regular division, but you put a decimal point directly above the decimal point in the number you're dividing. And you do that division exactly as you would do a normal division, except you need to put the decimal point right above where you see it in the number you're dividing. Here's another division that I've started for you. What happens if we divide 411 by 9? I start the division and I find it equals 45, but then I'm not done yet. It looks like it's going to keep going. Typically, I could say the remainder is 6, or it's 45 and 6/9 that I could reduce to lowest terms in terms of a fraction. But now for a decimal, I'm going to put 0.00000, and I'm going to keep going with the division. Going to put the decimal point directly above it, bring down the 0, and try 6. I see that's 54. If I do that subtraction, I get another 6. Bring down the 0. I get another 6. Bring down, it's 54. And notice what's going to happen. I'm going to get a repeating decimal that's going to give me 6s out as far as you can go. One way to deal with this, for example, might be to round it to the nearest hundredth and get 45.67. But because this occurs so frequently when you're dealing with decimals, there's actually a special notation we use for a repeating decimal, and it's this. I could express the quotient, the result of the division, this way: 45.6 with a bar over it, and that bar indicates that that 6 repeats forever in the decimal expression. In some cases, it might be better to round it off if you're dealing with an actual problem. If you want to express the answer absolutely to the fullest extent, you use the bar. And whether you would round it or use that bar over it to indicate a repeating decimal depends upon the nature of the problem. Another thing we need to do is often to change a fraction to its equivalent decimal. For example, if I have 3/4, that actually means 3 divided by 4. I can do that as a division and take 4 and divide 3 by that. And of course, in order to do it, I can't, 3 doesn't go into 4 at all, so I need to express it as a decimal. How many times does 4 go into 30? 7 times, 28. How many times does 4 go into 20? 5 times, and it's even. The decimal equivalent of 3/4 is 3 divided by 4, or 0.75. In order to deal with any fraction and change that fraction to a decimal, you divide the numerator by the denominator and express it, do that as decimal arithmetic, and express it as a decimal. 3/4 is equivalent to 0.75. To review, if you have this fraction a over b, the decimal equivalent is gotten by taking a and dividing it by b, exactly as we have done in the previous example. Here's another common problem that you might run into dividing decimals. Here I'm dividing a decimal, 76.42, by another decimal, 0.037. We know the procedure for dividing decimals by whole numbers. What we need to do is make 0.037 into a whole number in such a way that it doesn't wreck the problem, that you get the same answer. What I'm going to do is successively multiply the 0.037 by factors of 10 until I have a whole number. In order to keep the problem the same, I need to do the same thing to the number I'm dividing. Let's try it. I multiply both numbers by 10. Don't have a whole number yet in the number I'm dividing by. 100, no, not yet. How about 1,000? Aha, I'm done. So what I've done is, in both cases, moved the decimal point to the right 3 places. Now I'm dividing the number 76,420 by 37. The answer will be the same, because if you think of that division as a fraction, what I'm doing is multiplying the numerator and denominator by the same things, by 1,000, and I haven't changed the value of the fraction. The same thing applies here. Now I put the decimal point there, and I can continue to do this as a division. 37 dividing 76,420. I put the decimal point there, add zeros, and when I do this now, I get 2,065.405 as the result. If you're dividing by a decimal, you just need to keep moving the decimal point in both of the numbers to the right, the same number of places, until you're dividing by a whole number, and then you know what to do. Then we talked a little bit about irrational numbers, numbers that can't be written in the form of a ratio, a over b, in the form that looks like a fraction. And we saw that sometimes when we deal with square roots are irrational numbers. They can't be expressed easily. They're going to be a lot of decimal places. The easiest way to express those is by using your calculator. And there are a few tricks. For example, if I have the square root of 0.0009, I can change that to the square root of 0.0001 times 9. Then that's equivalent to the square root of those two things separately. And I can only do this when there are only multiplications or divisions involved. If there were pluses or minuses in there, all bets would be off. Then I can take the square root of each one of those separately and get a final result. However, there's something else that you need to see. First, that if you have a perfect square, you see that the number of decimal places in the square root is half what you started with. In a sense, it's the opposite of multiplication. Sometimes you can't do that. This looks very similar, and we can split it this way. What we find is we can take the square root of 9, that's 3, but there's no number that you can think of offhand that's not a perfect square. You need to use your calculator. When you do that, you find to the nearest couple of places it's 0.032, and then you multiply that by 3 to get your final result. Since we're talking about division, let's go back and examine scientific notation. We see that 100 is 10 squared, 10 is 10 to the first power, 1 is 10 to the 0. Remember, anything to the 0th power is going to be 1. But now let's continue that sequence going the other way. we can represent 0.1 as 10 to the minus 1, or 1 over 10. Notice that 1 over 10 to the first power is 10 to the minus first power. 0.01 is 1 over 10 squared. That's represented as 10 to the minus 2. And we can continue this sequence. And we can use this idea of numbers getting smaller and smaller, represented as 10 to a negative exponent, to deal with scientific notation for things that are very, very small. Let's, for example, take something very small. How about an atom? That represents the number of inches. That's the diameter of some atom. You see, it's very small. What I need to do is, starting at the decimal point, count back until I have a decimal point between the 6 and the 4, because I want to represent it as a number between 1 and 10. I count back to there and I find 12 places. Since I'm counting smaller, I can represent that as 6.41 times 10 to the minus 12 inches. I can do the same thing as a rule. If I have 1 over x to the nth power, I can represent that as x to the minus nth power. For example, 1 over r cubed can be represented as r to the minus third power. Then I can use that in division of polynomials. I can divide the coefficients, but then I can say I have a to the 2 minus 4 power, because I'm dividing by a to the 4th. And I can say I have b to the 3 minus 5 power, and I can evaluate that as minus 0.82. 2 minus 4 is minus 2. 3 minus 5 is minus 2. Or I can represent it that way, because things to a negative power actually can be written as 1 over the power. This brings us at last to material we've just looked at. Let's review it very quickly, because it's important. The Pythagorean theorem. The square of the hypotenuse is equal to the sum of the squares of the other two sides. This lets us, if we have a right triangle, knowing any two of the sides, calculate the third one. We've looked at the area of a triangle, a half the base times the height. We've looked at the information regarding circles, the circumference, the area around the circle, in terms of pi, the ratio of the diameter to the circumference, which is about 3.14. We've looked at getting the volume of cylinders, where we use the area of the base, which is the area of a circle, times the height of the cylinder. And finally, we've looked at finding the volume of a sphere. This